Hello everybody. Today we discuss multiplication and division. You may have wondered we were discussing addition and subtraction and we have not touched multiplication and division. One reason is it is very complex, okay, and you need actually repeated number of addition and subtraction, and we were discussing combinatorial circuit. So there are other ways, other approaches using sequential logic circuit concept to arrive at these two, but let us venture into a combinatorial circuit based binary multiplication approach, and similarly for binary division in this particular class. So in the beginning we shall look at the concept of binary multiplication and division, and then we shall look at the one such circuit, logic circuit. Okay. So binary multiplication, if you understand, is if you are multiplying similar to decimal multiplication, here only we are using binary digit. Okay. So if you are multiplying 0 with 0, so the result will be 0, of course. 0 with 1, it will be 0. 1 with 0, it will be 0, and 1 with 1, it will be 1. So if we are looking at multiplicand x and multiplier y, okay, which are called both are called factor, and the result is the product, then if we put them in the form of a truth table, the relationship is x and y is your m. Okay. Now this is for 1 bit, right? But if you are increasing the number of bits, so here is an example of 4-bit multiplicand multiplied with 2-bit multiplier. So the example is taken is of 13 and 2, so it is 26, we know, right, in from decimal multiplication. So here how do you do? First you multiply with 0, dy would have done in the case of decimal multiplication. So 0 multiplied with 1 1 0 1, this will be just 1 bit kind of thing. Each of this is a 1 bit operation. So this is the AND operation that you do. So it is all 0, right? Then we shift it. I mean, when so this we do not consider this particular place. At the next position we have 1 multiplied with 1 1 0 1. So this is 1 1 0 1 only. So this is what we are having now. So 0 directly comes here as the m0, the value in the first place, units place, and 0 1 1 0 0 0 1 0 1, and this is 1. Okay, if there is a carry, then we will add it. I mean, this is normal addition. Is it fine? And we can see this number to be what? This is 16, this is 8, 24, and this is 2, 26. It works, isn't it? And if we want to look at example with carry when we are doing the multiplication. So basically this is 13 with 3, it is 39, right? So 13 13 remains, this is 1 1, 3 we are multiplying. So this is your 1 1 0 1, this is your 1 1 0 1. So this 1 directly comes here, and rest we have to do by going through the addition process. So 0 1 1 1 0 1 1 1 0, a carry is generated here. So this carry and this 1, so 0, and a carry is generated here. So this carry is the final carry, and you can see this to be 32, and these 3 together is 7, we know. So 39. Is it fine? Similarly for 4-bit into 4-bit multiplication, if you are looking at, then we have got an example 1 1 0 1 with 1 0 1 1. Okay. So 13 into 11, so this is 143 in decimal. So here first with multiplication with 1 1 1 0 1 comes, then 1 1 0 1, it is just shifted by 1 bit. So this 1 will directly come here, then 0 is multiplied, so all 0, then finally 1 1 0 1. Then you do the adding, and if you perform that, you will see that it is coming this way. This is 128, and these 4 ones are 15, so 143. Is it okay? We have understood how binary multiplication is done in reference to decimal multiplication that we are already familiar with. Okay. Now, if we look at the hardware or the logic circuit for realization of this multiplication, So, first we look at 4 bit into 2 bit. Okay. So, in this case this is a 4 bit number. Now, it is generalized. Earlier we have taken specific examples. So, 4 bit number could be anything. So, which we represent using x3, x2, x1 and x0, and this is as y1 and y0. So, first we are multiplying y x3 to x0 using y0. So, that is end of this x3 with x3, x2, x1, x0 with y0 bitwise AND, right. So, this is represented here, this is represented here. Is it clear? Okay. And then this y1 ANDed with x3 to x0. So, this is there, right. And when you perform the addition, these two will be added and this will directly go as m0. Okay. And then this addition will come as m1 and there may be a carry and all those things will be happening. So, if you look at the corresponding circuit, one possible circuit, right. So, first a bank of AND gate, 2 input AND gate, right. One input of it is y0, in every case you see y0, right, and the other input is x3 in the first case to x0 in the last case, right. So, this is the AND output. So, this AND output directly goes this as m0, okay, and whatever is generated, this x1 y0 over here is to be added with next it is called partial product, okay. So, in this case this next case you see all of them are y1, this is y1, right, and this is x3 to x0. So, whatever is generated by this AND, right, x0 y1 need to be added with x1 y0, that is getting added, right, and with that whatever output is coming, I mean that is going here as m1 and the carry will be fed to the next place, this x2 y0 x1 y1 addition. So, x2 y0 x1 y1 addition. So, this is coming as carry from the previous stage and this output will be m2 and so on and so forth. This is the way it will go on. So, 4 if number of these bits over here is m and this is n. So, total m plus n number of bits are possible in the product. Okay. So, this we understand. Okay. So, now we look at little bit more complex thing. So, this is 4 bit cross 4 bit multiplication. Okay. So, that is why you see a little bit the complexity of it, for which we have reserved it towards the end of the combinatorial logic circuit related discussion. So, this is the way it has been arranged. So, stage by stage. So, we have if it was 4 bit by 2 bit, this is the bank of adder where we had ended the result. Now, 2 more bits are there, 3rd bit and 4th bit, for which you see another 2 such bank of adders are there. Okay. And this will give you finally m0 to m7, right. And to understand it, let us look at one example. Since this place is already clumsy, I have taken it to the right hand side, okay, but it will not be difficult to understand. And which example shall we take? So, we shall take that 13 multiplied by 11 example, okay, and we shall see that how it works in the hardware, right, in this particular array based arrangement. So, 13 x3 to x0 and 11 is your y3 to y0 over here. Okay. So, the first row this x3 to x0. So, this is your 0, this is the first row adder input that we are talking about. So, this is the first row adder input. So, this 0 is there in this particular place, right, and after that x3 y1. So, x3 y1. So, when we multiplied with all these things, it is 1 1 0 1, right. So, this is 1 1 0 1 that you get, and the other one is other input of the your this particular adder is x3 x2 x1 x0 ANDed with y naught is 1. So, that is also giving you 1 1 0 1, right. So, this 1 1 0 1 is a shifted version, you see here it is 0, right, and here it is not getting added with any 1. So, this is your 1 1 0 1, right. So, this 1 is finally directly going here as a output, right, for the product generation. So, these are the inputs of the this half adder bank of half adder that you are bank of adder you are having. The first one is half adder, rest are full adder. Is it okay? So, when you add it up, then what you see, this is 0 1 is 1, 1 0 is 1. So, this input of the hard, okay. So, this half adder, this full adder input is one of the input of the next adders, okay, next set of adders. So, this is the input to the next set of adder that is going as the adder output, okay. So, this is what you see in the next group. So, these are the adder output, okay, adder output from the previous stage. This is the carry that you get from the previous stage, okay. And then again you multiply it with what? Y2 with x3, x2, x1, x0, y2 is 0. So, it will be all 0. So, that is what you see here 0, 0, 0, 0, right. Is it fine? Then again you add it up and that addition result will come, okay. This addition result is coming here, this addition result is coming here, this addition result is coming here, this addition result is coming here. If there is any carry, it is coming, the carry is coming here, okay, right. And then again you and it multiply it with 1 with this 1 1 0 1. So, this is 1 1 0 1, okay. Then again you see the result. So, 0 1, this is 1 0 0 1 1 0, that 1 is coming over here carry 1 1 0 and this is 1, right. So, you collect all these 1 and that is giving you your final result, that is 1 0 0 1 1 1 1, okay. So, due to paucity of time, I mean otherwise you can put them over here individual places and see how it is happening, right. So, you have just placed it side by side, but you can in a bigger picture you can put all those values and keep adding it one after another, and you can find that you are able to arrive at this result, okay, and for other set of numbers also, fine. So, you can move to division, right. So, binary division, in this case we are having two outputs, okay. One is quotient, another is remainder, and the dividend is getting divided by the divisor, right. And if dividend is represented by capital D, divisor by small d, quotient by q and remainder by r, then this is what you get, okay. And how division can be implemented? It is similar to what you had done in your decimal division. So, if you take an example like say 1 0 1 1 is getting divided by 1 1, okay. So, first of all this 1 0 is small, right. So, even if you multiply, if you have to multiply it with a 0 only, leading 0 does not make any sense. So, this is 0 0, if you subtract you get 1 0 only, and then you take the next bit, okay. So, that is 1 0 1. So, now you have 1 over here, possibility is only 1 or 0, isn't it. So, 1 means this is 1 1, okay. So, if you subtract, this is 0, this is 1 and this borrow that you have taken. So, borrow was here. So, 1 1 it cancels, okay. So, you get 1 0, then you take the next value. So, basically this is 1. So, this is 1 0 1. So, again 1 goes there. So, 1 1, right, and then again if you subtract you get 1 0 and it stops here. So, your quotient is 1 1, right, quotient is 1 1 and remainder is 1 0, right. So, 1 0 1 1 is 11. So, what you have got is 3 you are dividing with 3, you got quotient 3 and remainder 2, which is fine. 3 into 3 plus 2, that is 11. Is it okay? So that was 4 bit getting divided by 2 bit. So if you have got a example with a bit bigger, so this is 7 bit getting divided by 4 bit. Okay. So the first case you take 1. So basically 1 1 0 1 here. So if you subtract, you get 1, right? Only 1 and 2 leading zeros, right? So you bring 1 1 from here, but then this number is smaller, right? So 0 you have to take as quotient. So this 0, so it is, if you subtract, you get only 0 1 1 only. So you bring next 0. So you still see that the number is smaller. So you have another 0 over here. So 2 zeros, right? So then subtract 1 1 0. Then you bring 1 from here, and this is 1 1 0. So this is a case where there is no remainder. So there could have been remainder depending on the value that is there. Okay. So the original number 1 1 1 0 1 0 1. This is 117, and you are dividing with 1 1 0 1, that is 13, and what you have got here is 9. Quotient is 9 and remainder is 0. Okay. Now to implement it, okay, we shall look at again an array based structure, right? And in this array we shall use at the cross point a unit cell. So this unit cell here looks something like this. Okay. So we shall explain it, what it is, right? And we shall see one example, of course, the way we had seen before. And so for that, so this unit cell has got what you see here, a input x and y, and this is a full subtractor, x minus y, full subtraction, that is there. Okay. Subtraction we have learnt using 2's complement, right? But we can have standard subtractor, full subtractor circuit as well. Okay. So for example, this is a full subtractor truth table. Okay. So this is borrow in, this is borrow out, this is the difference, and this is x from which y is subtracted. Okay. So 0 0, this is 0, 0 1, x minus y you are talking about. Okay. So 0 1, so difference is 1 and borrow is 1. Okay. 1 0, this is 1, no borrow is required. 1 1, this is 0 0. So this is 0 0, but there is a borrow from the previous stage, borrow in. So basically it is 0 minus 1, that particular case. So this is 1 1. So this is 1 1, right? So that's basically 0 minus 2, it becomes 1 plus 1 becomes 2. So if you take a borrow from the previous stage, so this is borrow, right? So borrow is 1 means 2, it becomes from the previous stage because it is a higher place. So the difference is 0. So 1 1, this is 0 0 and 1 1 1. Okay. Then basically 1, and you are taking a borrow, so it is becoming 3, 3 minus, this is 1 and 1 2. So basically 1 borrow and 3 minus 2 is 1. So this is the way you can get the truth table. And if you look at now the relationship, you will see that the difference is coming for the cases where there is only odd number of ones. Here, here, even number of ones, so this is 0. Okay. So again here, again here. So basically this is XOR between x, y and b in. And similarly, if you look at b out, it is x prime y plus x prime b in plus y b in. It is similar to carry, but in this carry generation case, this was not x prime and this was c in, carry in. Okay. So this is the way we can get the full subtractor circuit, right? Fine. Now this full subtractor, there is input b in and there is the output b out. Okay. And then this full subtractor output goes to a 2 to 1 multiplexer. Okay. So there is a select line, one select line, right? 2 to 1 multiplexer circuit, and the relationship we already know. So if this is 0, if the input over here is 0, then x is passed as the unit cell output. There is the catch, there is the nice thing about it, the full subtractor algorithm or the approach that we shall see. Okay. So if it is 0, then this one, what is to be subtracted in this particular cell, that only gets passed, not the subtraction result, not the difference. Okay. And if this is 1, then the difference gets passed. The difference gets passed. So this is what we need to take note of, and this is the thing. Okay. And what the other output is, see that whatever is being done here, okay, same information, same select input is going to the next stage. So there could be other such cell which is asking for same kind of select input for the multiplexer for that particular stage. Is it clear? So borrow out, borrow in the number from which this number to be subtracted, and finally the result, which is number from which it is subtracted or the difference, okay, depending on the select input, right. And this is the way we represent the unit cell, right. So these are the corresponding inputs. So borrow in, select output, select input, borrow out, this is number to be subtracted, this is subtrahend, this is minuend, and this is the output, whether it is minuend or the difference. Okay. So again with complex circuit, right, but this is doing a division of a 7-bit number by a 4-bit number. Okay. If you want 8-bit number to be divided by 4-bit number, then one more stage here, over here, need to be added. Okay. So that is the way it has to be seen. Okay. And you see that the arrangement is the way we normally divide. We divide from the higher bit. So D6 is here, D6, D5, D5, D4, D3, then D2, D1, D0. So gradually it is making a right shift. Okay. So in sequential logic based circuit development of multiplier and divider, the kind of shift it is required, left, right, these are all taken into consideration. Okay. This is the circuit, right, and now what you can see that this borrow out that was getting generated, that borrow out, its inverted form is actually getting fed as the select input of the multiplier. Okay. So in the final stage, if a carry is generated, so this is 1, so this is, then it will become 0. Okay. So when carry is generated, then if you go back, if it is 0, then the number from which it is subtracted, is minuend will come here, and otherwise the difference will come. Is it okay? So this is what is the case, and this inverted part of the carry, okay, is what is going to give you the quotient, and this is what is going to give you the remainder. So this is the way remainder will come. Okay. So this is the algorithm which has been arrived at and given a shape through a unit cell based array divider circuit. Okay. So now we can to appreciate it, let us quickly go through an example. Okay. So the example we take is the same one that we had taken before, that is 117 divided by 13, right. So so this is the dividend and this is the divisor. Okay. So dividend, then these bits D6 to D0, these are there. So first we shall take up D6, D5, D4, D3. So this is 1, 1, 1, 0. So this is D6, D5, D4 and D3, that is in blue. Okay. And divisor is 1, 1, 0, 1. So this is divisor, that is in brown. Is it okay? Then what you are doing? We are doing the subtraction, and in each of the subtraction we are looking at the borrow. So 0, 1 is subtracted from 0. So this is 1, right. So this borrow is coming over here 1 1 0, right, 1 1 0 again 1 1 0. So final carry is 0, right. So its inverted is 1, so that is your Q3. Okay. So this is 1, right, and this is the borrow out, the final that is getting generated, that you can see. So when Q3 is there, so the difference result will be going to the next level of subtractor this thing group. Okay. So what that is what you can see here. So this is your 1 1, this is 0 is coming here, this subtraction is 0, this subtraction is 0, right. In this case the subtraction result was 0 to subtraction, it was 1, so 1 is coming here. Okay. So these are the bits that you get for the minuend, and for the subtrend, so first place it is 0, so that is the 0 over here, and next is your D3, D2, D1, D0. So 1 1 0 1, and for this particular subtractor over here, so D2 gets introduced, D6 to D3 was there, so D2 is getting introduced here. So this is in blue. So D2 is 1 1 0, then it is 1, so this 1 is coming over here. Is it fine? So next you do what? Next you do again subtraction of this particular set, right. So this is your you are here, so 1 1 0, so 0 to 1, this is 1, 0 minus 1 is 1, borrow is 1, 1 1 0, this is 2, right. So there is a, this is 0, so this is again 1, so this is 0 minus 1 is 1, and then there is a borrow out which is 1. Okay. So this is there is a borrow out, so then its inverse is 0, so this is your quotient Q2. Okay. So this inverse is now going to the multiplexer input, all these multiplexer input. So when it is 0, then the minuend, not the difference, will come to the next level of full subtractor. Okay. So here this result 0 will not come, so this 0 will come over here. Okay. So this 0 will come over here, this one will come over here, and this one will come over here, not the difference result. Okay. That is what we have seen, the operation of the multiplexer. So for now the this particular subtractor, we are having 0 introduced from as D1, and what is to be subtracted is again this 1 1 0 1 in the brown. Okay. And for this particular case it is 0 only, right. Fine. So then again we perform the subtraction and see. So 0 to 1 we have a borrow of 1, so 1 1 it is 0, 1 1 it is 0, 1 to 0 this is 1, right. Then 1 to 0, this is again 1, and then there is a borrow 1. Okay. So again there is a borrow 1 that is present. So its inverse is 0. So you get Q1 also, and then again this is 0. So what you will see, the minuend coming to the next level of subtractors. Okay. Not the difference result. So that is what is coming over here, right. 0, this is 1, this is 1, this is 0, and this is 1 is coming as the D0 bit. So we have got 1 1 0 1, and over here is 0. So to be subtracted is D3 to D0. So this is 1 1 0 1. Okay. Now if you subtract, right, you see that this is 0 0 0, all of them are 0, and the borrow is 0. So its inverted is 1. Okay. And had there been some number present, that would have been the remainder. So remainder here is 0, all zeros, all I mean R3, R2, R1 and R0. Okay. These are 0 0 0 0, right, and your Q3 to Q2, Q1, Q0. So, this is your Q3 and this is Q0. You take all the borders, right. So, 1 0 0 1. Okay. So, this is the way it is done. You can try with some other number also, right. And wherever you have seen that only 0 is getting added or the first stage, instead of full subtractor we can have half subtractor. Okay. We have not discussed that logic, truth table or the circuit, but you can similarly get it. Okay. Fine. So, with this we come to the conclusion of this particular class. So, product from binary multiplication of two 1-bit number is obtained from logical AND operation of the numbers, and for getting more than 1-bit numbers, the multiplication result we can get by adding the partial products after appropriate shift, and the combinatorial circuit to get a multiplier performs that shift within the arrangement. Okay. And binary division will generate quotient and remainder. It involves subtraction and of divisor after again appropriate shift. So, the combinatorial circuit for that using cell array performs that shift within the arrangement, and as we discussed that it can be done by sequential logic circuit by some other arrangement which in certain sense can be considered efficient in certain context mode. Okay. And that we shall take up later. So, thank you.